All right, after that video, let's go ahead and talk about the notes for nuclear energy. And I'm actually not going to start on the top of the notes. At the top, there is a big table that involves fission and fusion. I don't want to talk about those till we get more into what goes on in the nucleus with this nuclear binding energy thing. So here's the table. Let's go past the table and let's talk about this nuclear binding energy. So Derek talked about this mass energy equivalence, and we know that the law of conservation of mass says that mass can either be created or destroyed. We know that energy can either be created or destroyed. And now the truth is there's this mass energy that they're both combined, that mass energy can neither be created or destroyed. It only gets transferred from one form to another. And so this equation that Derek talked about, E equals mc squared, it describes that mass energy equivalence, that the energy that comes from the sun, and realize this only happens within the nucleus. The energy that comes from the sun is the result of the incredible amount of mass that gets converted into energy. So when you have nuclear reactions occurring, this equation tells us that the mass in the nucleus gets converted into energy, and because it's multiplied by c squared, c is the speed of light, it is a lot of energy. And that's the big key. The reason why nuclear energy is so interesting and important environmentally, economically, politically, is because the nucleus represents a lot of energy. Remember, 99.9% of the mass of the Earth is in the nuclei of atoms. With this equation, with nuclear reactions, we're actually accessing that mass. And since that mass can be converted into energy, that means we have a lot of energy that we can get out of the nucleus. The other part of this slide is what I already talked about in the first video, where we talked about the strong nuclear force inside the nucleus. And you got to know the strong nuclear force is the force that holds the nucleus together, and the repulsive electrostatic force between protons is the force that tends to rip the nucleus apart. So E equals mc squared. We're going to do a problem like that in just a minute. Down below, this picture in the next chart just talks about the seesaw picture. Tells you that the energy in the sun is the opposite of the mass. If mass increases, energy decreases, and vice versa. Really, it should be the other way around. When the mass goes down, the sun loses, I think it was 4.3 billion kilograms of mass every second. All that mass is getting converted into energy that radiates from the sun in the form of electromagnetic radiation. All right, so let's look at these two sample problems. So this says, what's the maximum amount of energy that can be obtained from 650 grams of uranium? First thing I want you to see is we don't like grams. This is a mass of uranium, and it's got to be in kilograms. Grams to kilograms is 3 to the left. So 0.65 kilograms of uranium. We want to find energy, and so the equation is E equals mc squared. Don't you feel cool to be using Einstein's equation? Let's do this. So energy equals 0.65 is the mass. C is 3 times 10 to the 8th, and it's squared. Don't forget the squared, it's very important. Put that in your calculator. 0.65 times 3 times 10 to the 8th squared. 5.85 times 10 to the 16th power. This is energy. Units for energy are always joules. You may not have, this is obviously a big number, and you may not have much of a frame of reference to know exactly how big it is. So let me tell you. 1 bolt of lightning is 5 times 10 to the 9th joules of energy. And I want you to see if you can figure out how this compares to this. And a lot of people say, well, this energy is almost double this, because they look at the 9 and the 16. It actually isn't. If you double 5 times 10 to the 9th, you get 10 times 10 to the 9th. You're still in the 9th power. This is 7 orders of magnitude greater. In other words, it's a lightning bolt times 10 to the 7th power of energy. We get all of that energy. If we could get, this is how much energy is in a lightning bolt. If we could harness it all, we get a lightning bolt times 10 to the 7th from 650 grams of uranium, about a water bottle's worth, if that. That is a huge amount of energy. And at this point, you need to understand this is why nuclear energy is so attractive, because we can get a ridiculous amount of energy from a very small amount of mass. I heard somewhere one time that if we look at coal-powered energy plants, which are considered to be bad for our environment, we're trying to get away from coal power. A coal-powered plant is powered by about 14 train loads of coal per week, right? That's a coal-powered plant. 14 train loads of coal per week. No, sorry, one train load of coal per week with 14 cars. 14 cars full of coal per week. So 14 big train cars, you know what a train car looks like. 14 of those puppies being dumped into the coal plant every week to provide power for an average sized city, let's say. A nuclear power plant, to provide the same amount of power, all they need is two about 10 foot long, a foot or so in diameter, rods of uranium every year and a half to produce the same amount of power. This is obviously much less mass than this is. And the reason is, folks, is because we're dealing with nuclear energy here. We're accessing actually 99.9% of the mass, whereas a coal-powered plant, this is only electron-driven reactions that are occurring. That's 0.01% of the mass that we're talking about. So there's a lot more energy with a coal power plant that is left in the nucleus that's not accessed. When we're accessing nuclear energy, we get a lot more energy out of very few natural resources. Of course, the downside to nuclear energy is that it has to be precisely maintained, precisely controlled, and if it isn't, it can get out of hand very easily. And these elements are radioactive. It can cause death, it can cause health problems. A lot of nasty things happen. Second problem, actinium has 6.2 times 10 to the 12 joules of energy. What is the mass of the sample? Once again, E equals mc squared. The energy is 6.2 times 10 to the 12th. Solving for mass, and C is 3 times 10 to the 8th squared. Divide by 3 times 10 to the 8th squared. And if you do that, 6.2 to the 12th divided by 3 times 10 to the 8th squared, you get a mass of 6.89 times 10 to the negative 5th kilograms. Once again, I want you to realize that's a small number, right? That's a small number. We can convert this to grams, and you get 0.07 grams. If you have an idea, I don't know if you have an idea about how small 0.07 grams is or not. Got a paper clip right here. 0.07 grams is about 1/14 of this. From that much mass, much less than a paper clip, 6.2 times 10 to the 12th joules of energy. That's 4 orders of magnitude greater than a lightning bolt, greater than an average lightning bolt. So lightning bolt times 10 to the 4th is what we're getting from 0.07 grams. There is a lot. Like, it doesn't even make sense to say that. There's a crazy, massive amount of energy bound up in the nucleus. And if we can access it carefully and correctly, we can get a lot of energy out of it. So that's why nuclear energy is so attractive. All right, so let's go back up to the top of the notes now, and we need to talk about some nuclear reactions that happen. There are actually 4 nuclear reactions or processes that occur that you need to know about. These are the big ones. These are the 2 that you need to know about. These are big nuclear reactions, fission and fusion. We get lots and lots of energy from these. This is where the nuclear energy really comes from. Let's start with fission. Fission happens when a heavy nucleus splits into 2 lighter nuclei. This is the process that happens in a nuclear power plant, and this is the picture of the nucleus that's being split into 2 nuclei. Understand that the red and the black inside this nucleus, those are protons and neutrons. We know those are in the nucleus. What isn't shown here that's really interesting is that in every fission reaction, every fission event, there are anywhere from 2 to 3 neutrons that get ejected from this larger nucleus every single time. And this only happens with heavy nuclei, by the way. Heavy elements, typically elements heavier than iron, it can undergo fission and split. But every time fission happens, you get 2 to 3 nuclei ejected from this nucleus. Well, each liberated or ejected neutron is ejected at a very high rate of speed, and it'll collide with another nucleus, and that process, or that colliding, will cause that nucleus to split potentially, and that nucleus lets go of 2 or 3 neutrons, and each of those 2 or 3 collide with another nucleus and make those nuclei undergo fission, and it happens over and over again. You get this exponential chain reaction that happens. For that matter, fission is a process that is it's an exponential chain reaction, as I just said. It is, once it starts, it's unstoppable. It's practically unstoppable, which is part of the reason why nuclear power plants require precise, very careful controls, because this thing can get out of hand very quickly. But again, every time this happens, every time you get a fission event, there is a lot of energy that is released from the nucleus in the form of light, in the form of heat, in the form of electromagnetic radiation. Lots and lots of energy is released. So that's fission. Fission happens when heavy nucleus splits into 2 lighter nuclei. Fusion is the opposite process. Fusion happens with light elements, lighter nuclei, like helium and hydrogen are the lightest ones. It's when those 2 lighter nuclei fuse into a heavier nucleus. It can also happen with single protons. Fusion happens when 2 lighter nuclei fuse and become 1 heavier nucleus. With both of these events, the element itself actually changes. In the video about the sun that you watched from Veritasium, he talked about the protons going around inside the sun at a high rate of speed, and that's what caused this process. That's true, as well as the enormous gravitational force of the sun. You need to understand that it's not even worth comparing the size of the Earth and the sun. The sun has such a massive gravitational field. And it's not even worth comparing the size of the sun to other massive stars like Sirius and Betelgeuse and Canis Majoris. The gravitational force is just ridiculous on those stars. And so it's the gravitational force itself that literally pulls inward, and it squeezes the protons together so hard, and it causes this fusion to occur. Again, it fuels the sun and the stars. It's hydrogen being fused into helium and other heavy elements, and it produces lots and lots of energy. That's why we see the light, we feel the heat from the sun. It's all because of fusion. All right, on the back side of the notes, we're going to talk about something that is pretty much completely unrelated to nuclear physics, and that's Max Planck. Let's go back to when we talked about electromagnetic radiation. This is just something you need to know, and we should have put it in with the electromagnetic radiation stuff, but we didn't. Max Planck discovered what you already know, which is that energy and frequency are related. Remember when we talked about the electromagnetic spectrum, there was, at the lower end we had radio waves, and then we get up to visible light, and above visible light we had stuff like, what was this? There was UV up here, and at the very high energy electromagnetic radiation in gamma rays. That was the electromagnetic spectrum. Point was, low energy, low frequency, high energy, high frequency. And so Max Planck is the one that discovered that, and this is the equation that he came up with to be able to relate the energy to the frequency so that we can actually calculate this. Energy equals h times frequency. Frequency is in hertz, energy in joules. H is Planck's constant, 6.63 times 10 to the negative 34. Very small number. You don't have to memorize it. It's number 80 in your chart. But it's just something you're going to have to learn to be able to solve problems with. So here's an example of a Max Planck problem. So the problems will say this says, what's the frequency of a photon? So you're looking for F frequency. Photon has an energy of 2.7 times 10 to the negative 19th joules. This equation, E equals HF, is the only one that relates frequency to energy. So it's just simply plug and chug like everything else we've done. 2.7 to the negative 19th is energy. H is 6.63 times 10 to the negative 34. And we're going to solve for frequency by dividing by 6.63 times 10 to the negative 34. All right, that cancels that out. 2.7 times 10 to the negative 19th divided by 6.63 to the negative 34. 2.7 e negative 19 divided by 6.63 e negative 34. 4.07 times 10 to the 14th. Frequency is 4.07 times 10 to the 14th. Frequency is always in hertz. And that's it. That's pretty much, you'll just have to work with that equation. That's about all you have to know about that one. Don't worry about this problem. We don't need to worry about it.